This video is a short lecture note on chapter 14.6 in Greenberg's book, which is on non-Cartesian coordinate systems and vectors in non-Cartesian coordinate systems. So a Cartesian coordinate system is essentially the naive coordinate system that we've been using, where I have an x-axis and a y-axis, and I can talk about a point at a given x and y value, and if I want to construct a set of vectors to describe motion or velocities, accelerations, or whatnot. As usual, going back to undergraduate dynamics, we can have unit vectors that point along the x direction or along the y direction, and it turns out that no matter where we are in the xy plane, those unit vectors will still point in the same direction. Okay, but it's not always convenient to use those unit vectors that point in the same direction. So we've already seen the example in this class of a polar coordinate system where we have r and theta. And in that polar description, let me switch colors. It's useful to use unit vectors that point radially away from the origin, and we'll call that the radial unit vector E sub r hat, and then a vector 90 degrees away following the right-hand rule that we will call E sub theta hat. And of course the E sub r and E sub theta vectors depend on where you are in the plane, because the radial direction at this point over here is different than the radial direction. Let me actually label those. So if I call this point A, if I call this point B, the radial direction at A is not the same as the radial direction at B, so the unit vectors ER hat actually depends on R and theta. Okay, similarly E theta depends on R and theta. And this is very much unlike the Cartesian case where the unit vectors don't depend on where you are in the plane. And so now we'd like to use that Cartesian description. So it actually turns out that if I use that Cartesian description to expand these other basis vectors, so I can write E sub r as a linear combination of I hat and j hat. So this is I hat cos theta plus j hat sine theta. You can see that using elementary trig. If I look at the two components of that vector, the horizontal component is cos theta and the vertical component is sine theta. And similarly, you can look at the other unit vector that's 90 degrees away, and that's going to be negative I hat sine theta plus j hat cos theta. So you can verify that this guy is 90 degrees away from that guy using the right-hand rule. Okay, so now we would like to express the time derivatives of a vector in the polar coordinate system. So any generic vector, I can write r as r E sub r hat. Okay, so in other words, if I've got some vector in the plane, say this is x, this is y, I have a point in the plane. Here's my point over here. So this is my vector r, and I can express that vector that points from the origin to the point in the plane as x times I hat plus y times j hat, or I can similarly just express that vector as the distance away from the origin times the unit vector that points in that direction. Okay, so in the Cartesian representation, it's easy to take derivatives. So if I first look at my Cartesian expression, r dot is just time derivative of x I hat plus y j hat. But I hat and j hat are just constants. They don't depend, the orientation of I hat and j hat do not depend on where I am in the plane. So this is just the time derivative of x in the horizontal direction plus the time derivative of y in the vertical direction. And I can go on and I can take as many derivatives as I want. I can take another derivative. So the second time derivative is going to be the time derivative by dt of this quantity, and you see I just take another derivative. So this is x double dot in the horizontal direction plus y double dot in the j hat direction. So the Cartesian description is very easy to take derivatives, but it's not always the most convenient. Certainly applications like radar tracking, it would be more convenient to write things in a polar coordinate representation. So now if I look at my polar expression of the vector, so r dot is d by dt. I'm just going to express it in my polar representation. So that's the distance away from the origin, and that's the unit vector that points along the distance away from the origin. And so now I can use the chain rule, because we just proved in the last video note from section 14.5 that if I have a product of two things and I'm taking a time derivative, I can use the product rule. So this is r dot er hat plus r er hat dot. So the point is that the radial unit vector, since we are moving in the plane, the radial unit vector does change. So er hat dot is not equal, in general, it's not equal to 0. It's only equal to 0 for moving in a radial direction, and the radial unit vector continues to point in the same direction. So it turns out we need the derivative of er with respect to theta. Okay, and so if we go back and we look at our definition for er spelled out in Cartesian form, it turns out that the derivative of er with respect to theta is I hat times the derivative of x. No, I'm sorry, I hat times negative sine theta plus j hat times cosine of theta. And it turns out that if we look at our expression for, all I did, I took this thing and I took derivatives with respect to theta of that. And if you take derivatives with respect to theta, it ends up being e theta hat. So the derivative of er with respect to e theta is just e theta. So this thing is really just e theta hat. Okay, so now fully expressing in terms of the chain rule, if I want the time derivative, so the time derivative of the radial unit vector is the derivative with respect to theta times theta dot plus the derivative with respect to r times r dot. And you can see that since if I move radially, I don't change the direction of the radial unit vector, that second term goes away. And finally, that's theta dot times e theta. We can do the same thing for the e theta unit vector, and it turns out that d by dt of e theta hat is equal to minus theta dot e hat r. Okay, so the moral of the story is that if you have a curve moving through space, that coordinate system is rotating, and the time derivative of the radial unit vector is the time derivative of the angle times the current vector that points in the tangential direction, and the time derivative of the tangent vector is the time derivative of the angle in the negative radial direction. Okay, so you can see that if we go back up to our example over here, going from point A to point B, I'm decreasing theta, which means I'm rotating that set of vectors ER and E theta in a clockwise direction. So ER is moving in the negative E theta direction, and E theta is moving in the positive ER direction. So you can kind of get that from looking at this picture right there. Okay, so that's for the first derivative. We can do that again, just taking the chain rule. So the second derivative, r double dot, I can just take time derivatives of this expression and that expression. And it will tell us at the end of the day that that's r double dot minus r theta dot squared in the radial direction plus r theta double dot plus 2 r dot theta dot in the tangential direction. Okay, you can compare that to the trivial Cartesian description of the acceleration vector, and so that's just x double dot in the horizontal direction plus y double dot in the vertical direction. And so since the acceleration vector in polar coordinates is so important, we have names for these terms. So the component of acceleration in the radial direction that's due to tangential motion is called the centripetal acceleration. So if you're moving around in a circle, there is an acceleration outward, and it's proportional, it's equal to the radius of the circle times the square of the time derivative of the angle. That's the centripetal acceleration. And then the other term here is called the Coriolis acceleration. Okay, and so that is the component of the acceleration in a polar coordinate system in the tangential direction, in the theta direction, that's due to motion, that's due to a change of the angle and a change in the radius. Again, Coriolis. So if you're moving outward, if you're standing on a merry-go-round and you're walking toward the edge of the merry-go-round, you experience an apparent force because of this apparent acceleration, and that is the Coriolis acceleration as you walk outward and your angle on that merry-go-round changes. Okay, and so in the textbook there's some discussion about how to do this procedure for other coordinate systems, including the spherical polar coordinate system, but I will leave that for an exercise for the reader. So this is this concludes our discussion of section 14.6 about derivatives of curves expressed in non-Cartesian coordinate systems.